Hello and welcome everyone to EEE241 lecture. This is going to be the first lecture after the introductory video that I've already provided you with. And this lecture will contain an overview of the vector concepts, the basic concepts and the notations, and things like position vector and distance vectors. And you already are supposed to uh, be familiar with those things, and things like dot multiplication, cross multiplication between two vectors and stuff. And this lecture will not be so complicated, and this will just be sort of like a recap video of what you already know. So let's get started. Well, you already know what a vector quantity is, right? Any sort of quantity which have a magnitude as well as a direction is called a vector. For example, force is a vector quantity, or the gravitational force. Of course, the gravitational pull is also a force, so it is also a vector quantity. Or electric field intensity, that you already know, that is a vector quantity. On the other hand, we have got the quantities that don't have any direction, only magnitude, and those are called scalar quantities, like your mass or time or temperature. They're scalar quantities. So we already know how to denote vector quantities, right? Um, so let's say A is a vector. We denote it as A bar or A arrow or whatever you like. And the magnitude of A can be written as the mod A notation, or you can simply write an A, and that will do for you. So if a quantity, if a vector quantity is force, we can show it like straight line a straight line with an arrow direction. Uh, this is the point the force is being exerted, and this is the direction shown. So this is a vector quantity. The length will be proportional to the value or magnitude of the force. We know those things very. Now, suppose A is a vector which is in a 3D space. I mean, this vector line, say this is a vector, this directs to any random direction in 3D space. So we can write A as AXI, AYJ, and AZK, right? You know about this notation already. Uh, and you also know what this I, J, and K means, right? These are called the unit vectors, and you already know that I vector denotes the unit vector along the x-axis, J denotes the unit vector along y-axis, and K denotes the unit vector along z-axis. Alright, you know that already. And the AX, AY, and AZ, they denote the component or projection of the A vector along x, y, and z axis respectively. So if I were to find the magnitude of A vector, I would simply apply this formula, right? We're supposed to know about it already, right? Remember? And if we were to find an unit vector along the direction of A, like this, for example, let's say this vector has a magnitude of 5 units. So a unit vector along A vector will be along this direction with a value of 1 unit, right? And how do we get it? If we were to find an unit vector along A vector, we just simply take A and divide it by its magnitude, right? That's how we get the unit vector along A. So these are some of the notations you already know about. Then you know how to add two of the vectors. Let's say A is a vector, B is another vector. How do we add them? We apply parallelogram rule, right? We just take the adjacent arms of A and B as the arms of a parallelogram, and we just complete the parallelogram, and we just take the diagonal of it. Uh, let's say the diagonal vector is C, so C is equals to A plus B, right? And you also know about the triangular rule of vector summation. Since this is B and this is a parallel line, so this can also be attributed B. So A plus B equals to C. So this thing still holds. And this is called the parallelogram rule. You don't have to keep that in mind. Apologies for the bad quality of the drawing. Okay, now let's get familiar with position vector. Let's say, for example, we have a point in 3D space named P that has its coordinates mentioned as x, y, z. So the 3D Cartesian coordinates has three axes, right? The x-axis, the y-axis, and the z-axis. All right. So if we were to get to the point P over there, we will have to we'll have to travel first from starting from origin along the x-axis. We have to travel a distance equivalent to x units, right? Then we'll have to travel y units along the y-axis direction, and then we will have to travel z units of distance along the z-axis to finally get to the P point, right? So we have the coordinates of P point. So the position vector means, so the vector that is directed from the origin to the point, to the P point, will be called the position vector of P. All right. So in this case, the RP vector, which is unclear in the picture, I suppose, the OP vector basically will be called the position vector of P. I mean, any vector that is directed from the origin to the point that we are talking about is the position vector of the exact point. So RP is the position vector for P, and we can write it as this notation, all right. Since you know the coordinates of P point X, Y, and Z, you know that you have to go X units along x-axis, y units along y-axis, and z units along z-axis. So we get this vector. So if we were to take the magnitude of this vector, this will just denote the distance from origin, right? So whenever you were taking a position vector of a point and take up its magnitude, it will give you the distance of the point from the origin. In the case of position vector, we were dealing with one point that we know the coordinates, and another point that is the origin, so 0, 0, 0. But what if we were to find the distance between two points that don't include the origin? Suppose there is a point P that is denoted by X, P, Y, P, Z, P, and there is another point that is denoted by X, Q, Y, Q, and Z, Q, and you were to move from P point to Q point. So obviously the displacement vector will be PQ vector, right? So if you were supposed to take the magnitude of PQ vector, that will just denote the distance between P and Q, right? There There is a way to calculate this distance, however. Suppose you know the position, the coordinates of P points, so you already know the position vector associated with it, right? Which is RP. And also, as you know the coordinates of Q vector, you know the position vector of Q vector as well. And according to the triangle rule, if you remember, the PQ, the triangle rule of vector subtraction, if you remember it, uh, the PQ vector will be OQ vector minus OP vector, right? That gives us RQ vector minus RP vector. Okay? Okay, here, let me tell you another thing. Whenever we have a vector, whenever we have a point that we know the coordinates of, we can write it as, we can write the position vector in this notation, or we can write them as this notation. All right, the notation won't matter that much. So if we write it as RQ to be XQ, YQ, ZQ, and RP as XP, YP, ZP, then only the like components will cancel each other, right? Like I can write it as XQ minus XPI plus YQ minus YPJ plus ZQ minus, sorry, ZPK, right? So this will be the PQ vector, basically the distance vector between P and Q, right? So in this way, you can calculate any displacement vector between 2 points using their position vectors, all right? You will just subtract the initial point's coordinates from the final point's coordinates, all right? And if you were to take the magnitude of PQ, you will find the distance between P point and Q point, right?